All right, now moving on to part two. So we have Andy's a freshman at Cal every day. He wakes up in time to his 7:30 alarm, chooses whether to go to class or back to sleep. And his choices from the previous day do not affect his choice later. And he goes to class 20% of the days. What's the probability that he goes to class on the fifth day? So this would follow the geometric distribution. We can write that as x, where the probability of success is 0.2. So the probability that he goes to school on the fifth day means that there are four failures, can be denoted by 1 minus 0.2 to the fourth times our probability of success, and that's A. For B, what's the probability that he goes to class after the fifth day? And we can kind of think of this to mean as all that it means is that he succeeds sometime after the fifth day. So like he goes to school on the sixth day, on the seventh day, on the eighth day. But it means regardless of what it is, it means that there are going to be five failures. So we can write this probability out as 1 minus 0.2 to the fifth. That's kind of like the same thing as saying that the probability that x is greater than 5. On to C, um, what is the probability that he goes to class on the fifth day or before? So this would be denoted as P of x is less than or equal to 5. And then we can use the complement of what we have from B. Probability that x is less than or equal to 5 is the same as the probability of 1 minus probability of x being greater than 5. 1 minus 1 minus 0.2 to the fifth. That is 0.68. Now on to question 3. This problem, we're going to explore how we can apply multiple distributions to the same problem. Suppose you're a professor doing research in machine learning. On average, you receive 12 emails a day from students when you do research in your lab. This number varies greatly. Which distribution was used to model the number of emails you receive from a student in one day? We can, as we know that we're the number of emails we're receiving over a given period of time, which is a day, this definitely seems like we should be using the Poisson distribution because we're kind of told, like we're given a time frame and we're told like how many times an event is happening in a time frame. So we'll write that out as, we'll say that it's Poisson distribution, and it's going to have a parameter where lambda is 12. Okay, on to B. What's the probability that you receive 7 emails tomorrow? And then also at least 7. So let's start with the easy one. Poisson, where x is 7, is the same as here we have, let's look back, lambda to the k, e to the negative lambda over k factorial, where lambda to the k is 7, e to the negative e to the negative lambda, that's 12 over k factorial is 7 factorial. Yep, that would be probability that x is 7. And then the probability that we receive at least 7 emails tomorrow can be denoted as the probability where x is greater than or equal to 7. And that's like represented as like the probability that x is 7, x is 8, and so on and so forth. But we can also write that as the using complement rule, 1 minus the probability where x is less than 7. And that could just be represented as like 1 minus the probability of x to the sixth, x minus x to the fifth, minus x to the fourth, x to the third, x to the second, x to the first. And that's a way that we can get rid of like the infinite sum there. I'll write that out, but I'm not gonna solve for it. X to the sixth, x to the fifth, x to the fourth, x to the third, x to the second, and then x to the first. All right, so now we're on to C. Looking at the month of April, which a lot of students are emailing you to secure a summer position, what's the probability that the first day in April is exactly that you receive exactly 15 emails is April 8th? And so let's think about it, right? That means we're told that you receive 12 emails every day on average. So let's first think about what's the probability that you get exactly 15 emails using our Poisson distribution and model that. So we have our lambda to the k, e to the negative lambda over k factorial. That's the probability that x is 15th, which um, approximates to 0.7239. That's the probability part of the way. And now we have to think about how that's distributed, which if you know that on the eighth, that you receive exactly 15 emails on the eighth day, so you are gonna, so you can say that you have 7 failures. So if we just write, like we say that p is probability of that x is 15, we could write this as like 1 minus p to the 7th times p, and then yeah, 1 minus 0.007239 times 0.007239 is approximately 0.04278. All right, now on to D. Calculate the probability that April's the first day we receive at least 15 emails. So our probability P will stay the same as above, but now we're looking at the probability we'll receive at least 15 emails. So you can model that as x is greater than or equal to 15. And say that is the first day that you receive at least 15 emails. Which would be that like our probability, actually our p would change because before our p was just when x is 15. Now it's changed to where it's x is 15 plus x is 16, and then so on and so forth, which can be modeled as, I'll write that out, e to the negative 12th, and then a summation from 15 to infinity, so to the k over k factorial, which approximates to about 0.22798. And then we're still looking at the probability that April 8th is the first day that this happens. So once again, we'll call this probability P, and then we'll say that 7 days passed where this failed, and then on the 8th day it happened. So 1 minus our P, which 0.22798. Sorry for the messy handwriting. Times 0.22798. And that's going to approximate out to 0.03726. And now on to the last part. What's the probability that you can receive at least 15 emails on 10 different days in April? So for this one, we can actually use the exact same P as we had in D. So that's going to be 0.22798. And on 10 different days in April, we can represent that using, we're just trying to see, we know that April has 30 days, and then we're saying that this happens on 10 days in April, but we just don't know which 10 days. So we know that we have a probability of success, and then we have a certain number of successes. So I think that this kind of is pointing us towards the direction of the binomial distribution. So we'll write that out. The probability that x is 10, and then by the binomial distribution, we have 30 possible days, choose 10 successes, times our probability to the 10th, times 1 minus p to the 20th, and then that comes out to 0.06446. And that's it for week 10. See you guys later.